All right. So picking up where we left off yesterday, we're going to start talking about angles now, which we had to understand lines, particularly rays, a little bit better because those are what make up angles. So we're going to start with the most basic definition, which is what is an angle? And it's the intersection of two rays at an endpoint. Sorry? Not to this definition. I'm going to write a diagram, a little diagram to the right of it, but nope, that's the definition. Nope, just that definition. Angles can be in the mix with a whole bunch of other things as well. So some might say, well, technically you get a bunch of angles if you intersect two lines. Yes, but when you go to identify them, you're really identifying them by the rays that create that specific angle. So we're just going to look at a very generic one here. So I'm going to put my endpoints, draw two rays from it. I'll label this one A, B, C. And the notation that you would typically see, especially if written in text, would be angle A, B, C, or there's a slight differentiation. Sometimes you'll see this symbol. I don't know why they can't just be consistent. They basically represent the same thing. They're describing an angle. Now, the order is only slightly important. For example, notice A, B, C follows the path of this angle. I could have alternatively said angle CBA. I would have still been describing the exact same angle. But notice I cannot actually name it angle ACB. That would be something entirely different. So the endpoint that they share always has to be the middle point in that name. Otherwise, you're talking about something completely different. Next on our list, vertex. So the vertex is the common endpoint of an angle. So in other words, where the two sides intersect. The common endpoint where the two sides intersect. So I'm actually going to get sneaky here, and I'm going to steal my last image. I know that's cheating because you guys have to rewrite it yourself. But that endpoint of the two rays that I was talking about just moments ago, in this case, B, is referred to as the vertex. So going back to what we said with angles, when you're naming the angle, the vertex has to be the middle point or the middle letter when you're naming it. It can't be the first or last because then you're talking about a completely different configuration. Next one we have here, some special types of angles. First one is probably the one that's discussed the most because it's most frequently seen in architecture, and that is a right angle. So a right angle is an angle with a degree measure of 90 degrees. An angle with a degree measure of exactly 90 degrees, no more, no less. We actually saw a few examples of these yesterday when we talked about perpendicular lines, because perpendicular lines, when they intersect, actually form 4 right angles. But if you're just looking at a single right angle by itself, I'm going to draw a horizontal, or excuse me, a vertical ray and a horizontal ray. And visibly or visually, the way you denote that it is exactly a right angle is that little square that we used yesterday where the vertex is. So I made a comment yesterday. Don't trust the picture or make an assumption unless it is clearly stated, clearly marked, or you yourself through some process are able to prove it. So in this case, even if an angle looks like it might be a right angle, if it doesn't have a little box there in the corner, or it's not said somewhere that angle such and such measures 90 degrees, don't assume, because it could be 89.9 degrees. Visually, you probably wouldn't be able to distinguish the difference, but then technically it still wouldn't be a right angle. So just be mindful of that. Next one on our list, an acute angle. So this is an angle that is cute. No, it's an angle with a degree measure that is less than 90 degrees. So anything that is more close, has a smaller measure than 90 degrees is considered an acute angle. So anything from like 0.0001 degrees to 89.99999 degrees. Those are all considered acute angles. For example, again, just a rough sketch here. I'll draw 2 rays fairly close together. I'm going to say this one's about 35 degrees. I don't know without measuring it. Again, .35 falls below that 90-degree benchmark. If you're guessing then, obtuse angle is probably going to be on the other side of 90 degrees. So it is an angle with a degree measure that is greater than 90 degrees. I'm going to put a little side note there. Actually, no, I'm not. Change my mind. Because technically, angles get a little bit weird when they get past a certain point, because some would argue, which point are you measuring? All right. So an example of an obtuse angle. Yeah. Draw two rays going pretty far away from each other. And I could say, again, just kind of making up a measurement here that's greater than 90 degrees. I'm going to say this is 140 degrees. Again, I didn't exactly measure it, but just for the sake of a visual aid to go along with this definition. Okay. Next one is a straight angle. Now this one's kind of unique. I'll show you why here in just a moment, but it is an angle with a degree measure that is exactly 180 degrees. This one's the one I want to put a side note on, AKA, so also known as a line. So we've talked about lines before. You've done them in algebra. Technically, a line is considered to be a straight angle with an exact measurement of 180 degrees. So the visual for that is going to be, I'll put a vertex here, kind of towards the middle. I'm going to make a horizontal ray to the right and a horizontal ray to the left. Put my other points on here for these two rays. I don't know, label them Q, R, S, whatever you want to name them. That is considered an angle. Now we're looking at it, we're thinking, it's just a line. Those 3 points are collinear. Also true. But if we were talking about angle measurements and we were trying to calculate things, we would say that that angle has a measure of 180 degrees, therefore a straight angle. Next on our list are congruent angles. So now instead of just looking at them singularly, how do they relate to one another? Congruent angles, similar to our congruent segments earlier or yesterday, are two angles that have the same degree measure. So two angles that have the same degree measure are considered congruent angles. So my little diagram here, again, try not to get too fancy, just enough to be able to see. I'm actually going to just be a little lazy here and name them by their vertex only. So I'm going to call this angle A. And I can rotate this. So just so they don't look like the exact same angle visually, well, name this one angle B. Thing of it is, though, both of these angles have a degree measure of 45 degrees, even though their orientation has them facing different directions. Their degree measure is still exactly the same. So there's two ways that we would denote this textually. Is we would either say that the measure of angle A equals the measure of angle B. The little m is not behaving like a variable. It's a shorthand way to say measure of angle, whatever the angle is named. Or we could say that angle A is congruent, which from yesterday, if you recall, it's an equal sign with a little tilde above it. So angle A is congruent to angle B. I would say of the two, I probably use this one more frequently, but both would suffice. Sure. So again, it doesn't, in order to be congruent angles, doesn't mean that they have to be exactly the same size in terms of the length of their rays, or that they have to be opening in the exact same direction. It's the measure in degrees from one ray to the other. That's the only condition. That measurement has to be exactly the same in order to be congruent. Next one, still drawing. It doesn't have to be perfect, just enough so you know that they're the same. I'm mostly interested in the notation down here. Okay. Gotcha. Next on our list here are adjacent angles. Adjacent angles are two angles that share a common side and vertex. I should say common ray. I think that would be more accurate. Share a common ray and vertex. In other words, we could say, I'll make a little subnote here. We could say that they are next to each other. So two angles that share a common ray and vertex. The diagram I have for that one, I'm just going to go ahead and sketch in an acute angle here. And I'm going to draw in a third ray just somewhere in between the two, not necessarily down the middle, because we'll have a talk about that here in just a moment. But I would say that angle 1 and angle 2 here are considered adjacent. They share the same ray there in the middle between the two. They're sharing it along with the vertex. Next one on our list, again, it sounds far fancier than what it's saying, but it kind of makes sense when you sit back and think about it. Very similar to the segment addition postulate we wrote down yesterday. The angle addition postulate basically says that if you have two adjacent angles side by side, like, well, adjacent are side by side, two adjacent angles, the sum of their measures equals the greater measure, so to speak. In other words, the sum of the parts equals the whole. But the fancy way of saying it, we'll say if angle ABD and angle DBC are adjacent, then we could make the following statement. Then we could say that angle ABD plus angle DBC will equal the big angle, which we'll see here in just a moment, ABC. I like that here, so it sticks out a little bit more. It's also important that you recognize they have to be considered adjacent angles. So I'll leave that there for just a second while you're writing that down.
I got a quick question.
Go for it, Tara.
So when you equal it, where does D go? Why does D go away?
You'll see it in the diagram. Yep, so hold that. If your question's not answered until or after the diagram's been drawn, let me know and I'll try to clarify it. It's not gone, it's just not part of the big angle we're gonna see here in just a moment. So what I'm going to do for this, so we have enough room to kind of see it, my big angle I'm talking about is going to be an obtuse angle, so rather large. Put my vertex right here, do a horizontal line or ray to the right, another ray off to the left, and then I'm going to put a third ray between the two. And when I go in here to label them, putting my second point on each of these rays, my one here on the left is going to be A, my vertex that they all share is going to be B, and the one here to the far right is C, and then the ray there in the middle is D. So in other words, as you guys are writing this down, what it's saying is the measure of this angle right here plus the measure of this other smaller angle right here, because they are adjacent, equal this big angle, which contains both of them. So the sum of the little parts equals the big thing in a very non-technical sense. So Tara, does that answer your question as to where the D went in the large angle? Okay. So it's still there, but it was used to define the two smaller angles, not the greatest or the largest angle overall. Any questions so far? Kind of just been rolling through these. It's a lot of terminology, which is why when it comes to like definitions and stuff, I'm going to provide you most of those things. I haven't decided yet for the test whether you'll use a little note card or whether I'll just give you a reference sheet. I don't expect pure memorization. I want you to at least be able to look at it and say, I recognize what it's describing here. Let me apply that knowledge further. Next one on our list, angle bisector. So an angle bisector is when you have a line or ray that divides an angle into two equal parts. So an example of what that might look like, and I'm going to use an obtuse angle just because it gives me a little bit more room to work with. So say I have this larger angle here. I'm going to eyeball best I can, cutting this in half. Now, again, because of human error and my sketching abilities and our eyesight and all of that, it looks close to half, and without measuring it, we can debate it all day. But when I go in and add this next little feature, then it's beyond debate. It's me saying these are in fact supposed to represent two equal parts. And what that looks like, similar to what we used yesterday for congruent segments, we put a little arc between one angle and put one hash mark on it. And then we're going to put a second arc in the other smaller angle and put one matching little hash line through that one. And what that is saying, similar to what we saw yesterday with congruent segments, when we bisected a segment, those little notches say that these are congruent. So in this case here, those symbols, if we're doubting my drawing capabilities, which I would, is telling me that it is intended that those two measures are congruent, which means that ray there that's between the other two rays is considered an angle bisector. It is bisecting or cutting in half the large angle. Next one is not only a description of what vertical angles are, but a cool little trick that is always true. In fact, so true we use it a lot in several lessons going forward. First off, to describe it, vertical angles are two angles directly across from each other on intersecting lines. Now, here's the really important rule. This is just accepted as fact. Vertical angles are always congruent. Meaning, if you can prove or clearly spot that two angles are indeed vertical, you can then claim that they must therefore be congruent, meaning they have the same measurement. So what I'm going to draw here, it's going to be an X. Again, don't worry about how steep it is because this is going to work regardless. These are two lines intersecting at, it doesn't matter what angles they are, they're intersecting. What I'm going to list now are the pairs of vertical angles. So the one here on the left and the one here on the right are considered vertical angles. Therefore, off to the right, I can say angle 1 is congruent to angle 2. And I actually get a second pair from the top angle and the bottom angle. Those are also considered to be vertical angles because they are opposite each other, created from two intersecting lines. So I could say that angle 3 is congruent with angle 4. Now, it doesn't matter what their measures are. We could still make the statement that they are in fact congruent, regardless of whether they're really, really large angles or really, really small angles. Next one on our list, complementary angles. Complementary angles have to do with a unique relationship between two angles measurements. So this is when two angles complementary angles are two angles with measures that sum to 90 degrees. Little subnote here. They do not have to be adjacent. Meaning next to each other, which means if there's floating around this room out there somewhere an angle that measures exactly 30 degrees and a second angle that measures exactly 60 degrees, because those two angle measurements sum together to equal 90 degrees, we could define them as being complementary. Now, the diagram I'm going to use, I'm actually going to cheat and use a right angle, which is exactly 90 degrees to show this. But as the note there said, it's not necessary that they are adjacent. I'll do a vertical ray, a horizontal ray. I'm going to denote that this is in fact a right angle. But then in there, I'm going to go ahead and put a third ray and say that this is, the smaller one is 35 degrees. Therefore, the larger one must be 55 degrees. So those two angles would be considered complementary because they equal 90 degrees. Next one is supplementary angles. Very similar to complementary. These are another two angles. With measures that sum to 180 degrees. Again, the same comment applies here. They do not have to necessarily be adjacent. So just to kind of enforce that here, I'm going to kind of eyeball, try to draw 120 degree angle. Again, guessing about what that looks like. Say this is 120 degrees. And then I'm going to draw a second one. And say that this one is 60 degrees. So even though they're not adjacent, because if you were to add their two measurements together, that they equal 180 degrees, we could say that those two angles are in fact supplementary. And then the last one, very specific relationship here. These are adjacent angles. That are also supplementary. When they are combined, they form a line. So for example, here, say I have a, I don't know, similar to the one up above, 60-degree angle and 120-degree angle. Whoa. Because they are also adjacent, notice that their two rays that they do not share together form a straight line, or a line, I should say. So in other words, linear pairs are always supplementary, but supplementary angles aren't always necessarily a linear pair. But they do kind of go, they are related to each other. So that concludes most of those definitions, or at least the sketches along with them. Like I said, a majority of what you focus on today is going to be more of the lines, the planes, the points, segments, rays, things like that. The angles will come up again, I think, if not tomorrow, then Thursday, where we kind of really dive into them, because there's a lot you can do with angles. But before we finish, I want to look at the last couple pages here, which should go a little bit faster, thank goodness, as we look at some more detailed definitions of specific pieces you'll be using today, and then some examples that you'll then be working on your assignment. Yes, sure. So on this next page, again, I know we've defined most of these already at the very, very beginning. These are slightly more detailed with a little bit of extra information for us. So here, first one, point, which is identified there for us. A point is just a location. It has no size or shape. We always use a capital letter to name a point. So an example there on the image there next to it, we have point A. There's no, or at least not that I have found, no little symbol or mark that you can use to say point. Usually it's just the word point. Second one that you're going to use a lot today is going to be a line. So a line is made up of points, infinitely many, in fact. Usually we denote at least two so that we can name it. Any 2 points form a line. So literally you draw any 2 points anywhere in space. Those 2 points can be connected with one line. In fact, we'll learn later that that is actually the shortest path, is a straight line between 2 points. A line has no thickness. Or width. In other words, it only has a length. And to name a line, you do so by any 2 points that are actually on that line, or you may use a lowercase script, meaning cursive letter. So in the diagram there next to us, we can name it with the 2 points that are on it with a little line symbol above it. Notice that it does have to have the little arrow marks above it. Or you could describe it as saying line N. My cursive is kind of weak. That's supposed to be a cursive N, even though it looks more like an N. But yep, it's going to bother me if I don't fix it. I don't think I made it any better. Oh well. So line XY or line N are both describing the same thing in that image. Now, some sub definitions that we talked about again yesterday is the difference between collinear points, which are points that lie on the same line, versus non-collinear points, which are points that do not lie on the same line, but there must be at least 3, because 2 is not enough, because any 2 points form what? A line. So if you just have 2 points, they're always going to be collinear because they always form a line. 3 points, however, gives us the opportunity for them to not all line up. Next definition here is a plane. Most of us would describe a plane as being a flat surface made up of points. Now, any 2 points can form a line, but any 3 points can make a plane. A plane does extend indefinitely, forever and ever and ever, in all directions. So imagine a sheet of paper that never stopped going in each of the 4 directions. To name a plane, because 2 points usually define a line, you need 3 non-collinear points that are on that plane, or you can use an uppercase script letter. So in this case, we have 2 ways to define this one. We can either describe it as plane JKL, or we can describe it as plane and then use a cursive P. Again, I'm pulling this all from the diagram here that was provided for us. So J, K, and L are points on the plane. P is just the name of that plane, one of the ways to name it. Again, similar with collinear and non-collinear, we have coplanar and non-coplanar. So if all the points exist on the same exact plane, they're considered coplanar points. Whereas if one or more of those points do not exist on the same plane. So again, for example, imagine on your piece of paper on your desk, if I drew a bunch of points on that piece of paper, they are coplanar. They're all on the same piece of paper. It's a plane. But if I took, I don't know how I would do it, but something and drew a little point up here floating in space, now that new point is no longer coplanar because it does not exist on this sheet of paper. Now we've crossed over to a 3rd dimension, which gives us a whole new list of exciting things to do. Last couple things here has to do with what happens when intersections take place. The first one shouldn't be too much of a shock. It should come directly from algebra. And that's when 2 lines intersect. They intersect at a what? You may have said it. I just can't hear it.
Point.
At a point. That one's pretty clear to see because you can draw 2 lines on a sheet of paper and mark the point where they intersect. On the other hand, it takes a little of imagination, and I don't have a model or anything to represent it. When you have 2 planes intersect, they actually intersect at a line. Now that one again is harder to imagine because I'd have to like cut strips in this sheet of paper and slide them together. But if you were to trace where the two planes were touching, it would form a line. So two lines intersect at a point, two planes intersect at a line. All right, home stretch. This practice is going to make the assignment for today much easier, but there is one caveat I need to sketch in here up in the top margin. Answers may vary. Reason for that is it's requesting us to identify specific situations. In some of these diagrams, there are multiple examples of the same thing. So we're doing this section together, so odds are our answers will be the same. But if you look at it and say, well, what about this one? Just ask. Odds are it may also be an example of what's being described. So you have these diagrams there in front of you. I'm going to try to squeeze mine to fit onto the screen as well. First one, using the diagram here, can we name 4 collinear points? Almost. Careful though. I heard, so it has to be 4. All four, in order to be collinear, all 4 have to be on the same one line. HNKI. So again, there are examples of 3 collinear points, but the only line, which is line R here, has 4 points that are identified as HNKI. Can anyone find a line that contains point M? MNO. So technically with a line, you only need 2 points. So MN. So we would denote that with a symbol. Can anyone think of another way we could? Heard, I think. Line P. Again, remember naming lines, use a lowercase script letter. Or we could say line MO or line NO. There's lots of ways to name that one. What about a line that contains points H and K? Line R. I don't know how to do a cursive R by itself. I think it's like that. Doesn't look like theirs, but so closer to cursive than just regular font because it's supposed to be script text, which I say is closer to cursive if I were trying to describe it to somebody. Again, you could have said line HN, HK, HI, NK, NI, IN, KH. There's lots of ways you could have named that same line. So that's why I say answers may vary. What's another name for line Q?
Line JK.
JL, JK. There's a couple options there. KL, LK. There's all sorts of things. Any combination of 2 points on that line should be enough so long as you use the notation. So I don't know. I'm going to pick JK just because it makes me chuckle inside for childish reasons. Last one. Where is the intersection of lines P and R? At point N. Good.
So another name would just be those 2 letters, JK.
JK, KJ, JL, LJ, KL.
Like another term.
No, we're just naming it, not a different term because a ray and a line are different things. Now, technically, you could argue that two rays going in exact opposite directions make a line, and that would be an entirely different question. But yeah, this one's just asking for a name for it. Thank you for clarifying. Second one here, again, we have to use a little bit of our imagination just to kind of describe what's going on here. What we have is a plane. There is a line that exists on that plane, but there's also a line that's going right through it. Hence that kind of dotted segment. You kind of have to imagine a three-dimensional scenario here. So can we find a line containing point F?
DE.
Line DE, that'd be a good way. Or we could say DF or EF, or we could even say line J. So lots of options there. What's another name for line K? BC, okay. So BC or line K is that one that we have to imagine is going through our plane, going right through it. It's not actually on it. Can you name a plane containing point A? AE, ADE, okay. Good job remembering that in order to name a plane, you need at least 3 points, 3 non-collinear points. It's kind of hiding in there, but you could have also named it plane M, kind of sitting there on the corner of that plane. Couple options there. What would be an example of 3 non-collinear points?
BCK.
B, C, A. Good. So B and C are on the same line, but A is kind of off on its own thing on the plane. So B, C, A. Now, some of you are saying, well, B and C are on the same line. There's no way around that because remember, any 2 points form a line. Where is the intersection of plane M and line K? Sorry? Point E. So if this was existing in real life, I would imagine someone took a piece of paper and maybe stuck a toothpick through the middle of it. So the point where it's touching or where it intersected the paper would be the point we're looking for. Again, some of these answers could have other options. If you got something else and you're not sure and you want to check, just let me know. Third diagram. Use the diagram to identify the following. So 3 coplanar points.
BWR.
ZW, careful, R is the name of the plane. It's not a point. Logan, what did you say?
BWX.
VW and X would be an example. We could say, technically you could say WXZ. I know it looks like it's on a pyramid, but technically there is a plane going through that side. You could say WYV, VYZ, all sorts of things, all sorts of combinations. How about a plane containing point X? WYX, yep, that would work. Or I could have even said plane R. Where is the intersection of plane R and plane ZVY? This one's kind of tricky.
W.
So careful, 2 planes don't intersect at a point, they intersect at a line. So we're actually looking for a line or even a line segment. Well, you said Y and V? I would agree, because here is plane R is this kind of rectangular-ish looking one. ZVY is this left kind of side of the pyramid. They intersect down here at VY. Those are the 2 points that they share. So we would name that, in this case, I'd say segment VY. How many planes appear in this figure? This is kind of a trick one. Two, one. Getting closer. Now we're just guessing. There's actually 5. So imagine for a moment, look at the pyramid first. It has 4 sides. Each of those sides, technically it's 5 sides. The top 4 sides each are their own plane. Even though they're looking triangular in shape, only 3 points to make a plane. So those are 4 planes. Then the base of the pyramid happens to also be plane R. So identified in this diagram, there are a total of 5 planes. How many of those planes contain the point W?
3.
What's that? 3. Yep. So the base, so plane R contains it. And then the 2 sides nearest us on that pyramid also contain it. So VWZ and XWZ, those 2 planes contain it. So does plane R. Now we're getting real trippy. So now we have 2 separate planes. One of them has a line on it, but then it looks like we have a line that is intersecting both planes. Where is the intersection of lines L and M?
E.
Point E. What is another name for plane Q? I'm gonna do this one because I think it's funny. I'm gonna name it plane FIG. Fig. Are points D and E collinear or coplanar?
Collinear?
Collinear. Now, some might say technically they could be coplanar, but that plane is not being identified here. There would have to be a third plane inserted in there with a third point that's not collinear with those 2. So it gets a little trippy, kind of, I don't know, you have to wrap your head around it and be imaginative, but I would agree that these would be collinear. How many times do planes P and Q intersect?
2.
2, where at?
At E and D.
Line L intersects the 2 planes at D and E, but look at the 2 planes P and Q. Do they intersect at all?
No.
They don't appear to be. And if I were guessing, I would say they may even be parallel planes. So I would say 0. All right. So that's it for the notes for today. I'm going to wrap up the video here, and then we'll do our assignment, or I'll hand out the assignment.